So hopefully we'll cover those in this class. So here's one, and let me just go through one by one. Esterification is one of them. So let's quickly discuss esterification. So how are esters formed? So esterification. Now there are two ways of forming esters. So the first one, we're also going to quickly discuss the naming as well. Number one, the number one way of forming esters is, okay, what you do is you've got an alcohol plus a carboxylic acid, and they're going to react together. And that would result in a reversible reaction. In that reversible reaction, an ester and a water molecule are going to be produced, and that's a condensation reaction. So ester plus water is going to be produced. If you want to form the ester, the conditions for that reaction are, you need concentrated sulfuric acid and reflux. To vice versa break the ester, what you need to do is it's going to be dilute acid. So it's going to be either dilute acid or alkali. Plus there's going to be reflux. And that's pretty much it. That's what and the type of reaction, the forward direction, the type of reaction is known as a condensation reaction. So this one is known as a condensation reaction. And in the backward direction, the reaction is known as a hydrolysis reaction, that the molecule breaks down back into its two component reactants. So it's a hydrolysis, you're adding water to it. So we're going to do a couple of reactions for this. And remember, this is the first type of esterification. This is your O-level stuff. So you've got a carboxylic acid. And this is your carbon chain. On the other side, you're going to have an alcohol. Remember, the OH groups must be facing each other. So you've got your hydrogen atoms. So it's a propanol with ethanoic acid. So one of them is propanol, the other one is. So this one is ethanoic acid. And this one over here is a propan-1-ol molecule. Now what happens is, the reason why esterification happens in the first place is that this carbon has got a positive charge. And the OH over here, let me just keep the H separate. So the OH over here has lone pairs. So the lone pairs of the OH of ethanol are going to get attracted to, they're going to get attracted to the carbon, which is positive. And as a result, these things will get eliminated. The OH and H from the middle, they're going to form a water molecule. So the product that you're going to get is an ester. Water molecules are going to be formed. So the result of the reaction would be the formation of this ester. So I'm going to eliminate the H and the OH. This is no longer ethanoic acid. And the two things would now join up. They're going to link up. They're going to come together and they're going to link up in the middle to form that ester link. So that over here is your ester link. This entire thing is known as an ester group. Anyways, that's your total reaction, and that's about it. You need, the conditions are written above: concentrated sulfuric acid and reflux, and a water molecule is going to be produced as a byproduct. Okay, Saim, is this clear? Alicia, Zaib, clear?
Yes, sir.
Yes, sir.
Okay, so this is your O-level reaction. It's a water molecule is going to be produced as as a byproduct. How do you name the molecule? You name the molecule in two parts. You divide the molecule in two parts. One part would be your it's 3 carbon atoms, so that's prop. So one part is prop, the other part has 2 carbon atoms, that's eth. The alcohol side or the single O side, that would be vial. It's going to have vial at the end, and the double bond O side will have the O8 side at the end. So that's how you're going to name this, and the molecule name would now be called propyl ethanoate. So it's based on the number of carbon atoms. This side has 3 carbon atoms, that side has 2 carbon atoms, and you add weight at the end of the double bond O side, and the single O side, that would be vial. So that's the name of the molecule, is propyl ethanoate. And you'll be asked to draw all sorts of esterification reactions. So for example, let's say I have a scheduled formula of a molecule, and the molecule looks like this. That it's got an OH group. So it has this OH group. And this other molecule is a dicarboxylic acid. So this other molecule, let's draw that. So that one is so that one has two carboxylic acid groups. So it's got a double bond, it's got an OH over here, and it's got an OH over here. Now the question, and this is double bond O, and this one is double bond O as well. Now if you know how to read skeletal formula, that's a carboxylic acid. The carbon is double bond O and OH. This one over here is also a carboxylic acid. So they're saying that there are 2 molecules of this alcohol that are reacting with this dicarboxylic acid. So how would they react? The way they're going to react is, remember, the OH groups react with each other. So you have to bring the OH groups together. So if I want to write the product, I'm going to copy everything. So if I want to write the product, and they're saying that there are 2 of them. So this is, let's rotate this one. And there would be 2 of them. So there's another one over here. This one is going to react with this one, while this one will react with this OH group. And they're going to join together. So the OH groups would face each other. And what will happen is that the carboxylic acid would lose its OH, and the alcohol would lose its H. They're going to lose. Okay, let me just show you, just to highlight this. Where did the? No, just a second. So this one. So just to highlight this clearly in your notes. So what would happen is that the OH will be lost and the H will be lost. Over here, the carboxylic acid would lose its OH and the alcohol would lose its H. So the ester that's going to be formed would be, you just remove them and you connect them together. So that's what the ester is going to look like. So carboxylic acid loses OH. This loses H. This one loses OH. That one loses H. And you just link them. You just bring them together. Okay, just a second. I did it probably on the wrong one. So this one. So OH lost, H is lost. OH is lost, H is lost. And you just join them together, that's it. So that's one of your ester link that's formed. It's C double bond O and O. And here's this other one that's getting formed. So there are two ester links that are formed in this molecule. So that's one, and that's your other one. So that's how you're going to do this. Remember, the OH groups must face each other. Is this clear? Clear, Sanogo? Is this clear?
Yes, sir.
Yes, sir.
And so just another one. Let's say we have and there's a lot of examples of esters getting formed with the same molecule. They give a lot of examples like this. For example, they might give you this ester, this molecule, and they're going to say something like that this molecule over here is forming an ester with itself. And they would ask you to draw that ester. So this is how it's doing that. So there's a carboxylic acid here, and there's an OH on the other side. So this one has OH. So that's the alcohol side. And this other one is your carboxylic acid. That's double bond O and OH. So the molecule has two sides. And they say that the molecule, two molecules react under concentrated sulfuric acid. So two of them are reacting under concentrated sulfuric acid. Reflux is done and a cyclic molecule is produced. Now, concentrated H2SO4 is the specific condition for making esters. So two molecules are reacting together. So what I'm going to do is I'm going to pick two molecules. So that's one of them. The other one would be a rotated version of the same thing. Remember, the carboxylic acid must react with the alcohol. So the two OH groups must be facing each other. So again, what will happen is that the OH would be lost from the carboxylic acid, and the H would be lost from the alcohol. The OH would be lost from the carboxylic acid, and the H would be lost from the alcohol, and a water molecule is going to be produced, and they're going to connect together. So the product that you're going to get is going to be this thing. That it would look like this. That H is lost, OH is lost. OH is lost, and the H is lost. And the two would link up to form a cyclic structure. And that's an ester link. That is C double bond O with an O. This one is also C double bond O with another O. So I'm just going to draw these arrows now. So just make sure, remember how esterification happens. Remember that the two OHs would be facing each other. The OH would be lost from the carboxylic acid side, and the H would be lost from the alcohol, and you just bring them together. That's about it. That is exactly what we did over here. You had an alcohol, and you had a carboxylic acid. I put the two OH together. The OH is lost, the H is lost, just join them together. The alcohol, bring the alcohol and the carboxylic acid next to each other. The OH is lost and the H is lost, just put them together, and that's the molecule that's going to be formed. The same thing happens exactly over here. Is that clear?
Yes, sir.
That's another thing is that acyl chlorides make esters at room temperature.
Sir, sorry to interrupt you. Which molecule is the above one?
What's the name
What's
of
the name? Yes, sir, the name.
you don't. This one is a cyclic structure, so you wouldn't be able to name this. Okay? Complicated molecules, specifically esters, etc., they can't really be named properly. This one you can. This one.
No, yes, sir.
I said this one you can name. That's 1, 2, 3, 4 carbon atoms. So if I want to name this, it's bute. It's going to start with bute. It's a carboxylic acid plus it's an alcohol. Carboxylic acid has a higher priority. So it's a butanoic acid molecule. And the alcohol is at position number 4. So it's 4-hydroxy butanoic acid. I'm assuming there are 4 carbon atoms. That's 1, 2, 3, 4. So this is how you name molecules. That's naming of molecules, like 4 carbon atoms, that's bute. The main chain is named after the highest precedence group. Carboxylic acid has a higher precedence compared to the other ones. So instead of calling it butanol, you call it butanoic acid. And the position of the butanoic acid would be, this would be carbon number 1. So the OH group is present at the other end. It's at carbon number 4. So the OH group would be considered a branch. There's a branch that is attached on the butanoic acid molecule. Is that clear? On the 4th one, there's a... Okay. As the next one is, there's another way, the second reaction, there's another way of making esters. And that second reaction is, you can make esters using acyl chlorides. So acyl chlorides also react to make esters. And they do that at room temperature. Because remember, acyl chlorides have much faster reactions. We did discuss why would they have faster reactions. The reason is room temperature with alcohols. So it's the exact same esterification. There's nothing new. It's the exact same esterification reaction, except you're doing it with acyl chlorides. Now with acyl chlorides, the first thing is, what is an acyl chloride? It's C double bond O and Cl. And the reason the reaction happens to be faster is that the positive charge is a lot stronger in acyl chlorides. I mean, this is what an acyl chloride is. The carbon positive charge is a lot stronger. So carbon, so acyl chlorides, carbon has a higher slight positive charge density. And the reason it has a higher positive charge density is that it's bonded to 2 electronegative elements. So it's bonded to 2 electronegative elements, unlike carboxylic acids. In carboxylic acids, the carbon had a positive charge, but the carbon positive charge, it was only bonded to 1 electronegative element. The other side was an OH, which actually has an electronegating effect. So there was only 1 electronegative element attached to it. But now what you have is you've got a much stronger carbon positive charge. The rest of the reaction is kind of the same. You react an acyl chloride with an alcohol. Now an alcohol has lone pairs. So if you have an OH in alcohol, so it's got these lone pairs. Those lone pairs would be attracted, especially this oxygen has lone pairs. So those lone pairs will be attracted to this carbon, which is positive. And as a result, the H and the Cl, they get knocked out from the middle. That is what happens. So as a result, the H and Cl get knocked out, and the product that you're going to have is going to be an ester. It's going to be the same product, except instead of the Cl, the previous case you had an OH, but now you've got a Cl. And the byproduct, instead of being water, it's going to be So the H and the Cl, they get knocked out. And these two things, they join up. They join up in the middle. And they form the exact same ester link. Plus HCl is going to be your, HCl is going to be it's going to be your reactant. That's the only difference. Acyl chlorides would do exactly the same thing, just like carboxylic acids. So if I repeat one reaction, like instead, if I have like any of the reactions, if I have, let's just copy this reaction. Everything would be exactly the same, except that the reaction would be a lot faster. So if I just repeat this reaction, so if I repeat this reaction, instead of the carboxylic acid, I'm going to have Cl in its place. That's the only major difference. And instead of the OH getting knocked out, I'll have Cl getting knocked out. So over here, the Cl is the one that's going to get knocked out over here as well. Instead of the OH, I have a chlorine that's getting removed. And the end product would be exactly the same. I'll just get an ester link, that's it. So is this clear?
Yes, sir. Sir,
Haji.
is it possible that alkyl chlorides can react with phenols to make an ester bond?
नहीं उस पे मैं आ रहा हूँ ठीक है. So the third one is that one. The third one is, how do phenols make esters? Now the problem with, so basically it's just keep it simple. You had a carboxylic acid reacting with alcohols, but in that case you needed some conditions like concentrated sulfuric acid. Why? Because the reaction wasn't that easy. The carbon wasn't that positive and it wasn't that interested in the lone pairs of this oxygen. In the next one, in acyl chlorides, the carbon was slightly more positive because it was also attached to two electronegative elements. So it was more interested in that lone pair. So you had a slightly faster reaction. I didn't write faster reaction. Just a second. So this reaction is going to be faster. It happens at RTP. So it happens at RTP. Now the next one is, what about phenols? And how do they make esters? Now phenols are kind of very similar to alcohols. So let's talk about phenols. Number 3. Phenols, remember, only make esters with acyl chlorides. With acyl chlorides, they don't react with, they don't have a reaction with the normal carboxylic acids. So don't react with carboxylic acids. So don't react with carboxylic acids. And the reason for that is that when you have an acyl chloride, phenols have this big issue, which is that if I draw a phenol, the issue is that the lone pairs on the OH are actually missing because they overlap with benzene's pi electron cloud. So what happens is, you've got an OH, and there's a lone pair on this OH. But that lone pair isn't really there because that lone pair has kind of its charge density decreases because it mixes with benzene's pi electron cloud. So this other molecule, which is our acyl chloride, it's got to have a very strong positive charge. Only then can it attract the lone pair back again. Carboxylic acids are not able to do that because you have to pull the electron back. The lone pairs, the charge density is lesser. So what happens is charge density on the lone pair decreases. So it's lesser as it overlaps with benzene pi electron cloud. So it overlaps with benzene's pi electron cloud. And what you need to do is, so only acyl chlorides with a high charge, with a high partial positive charge density, or with a large are able to attract those lone pairs. Is that clear? Carboxylic acids are not able to do that. Is this clear? Saib, clear? Saim, is this clear? Munia, is this clear? Alicia, is this clear?
Yes, sir. Thank you.
Yes, sir.
Yes, sir.
Anyway, so phenols are only going to, just remember, phenols are only going to make, and the ester would be formed in pretty much the same way that you'll have, let me just, so the ester would be formed in pretty much the same way that the Cl would be lost and the H would be lost, and the two would link up. And HCl is going to be your byproduct. So the two of them would link up, they would join up in the middle. And that's your ester link. And the other byproduct is going to be your HCl molecule. So that's your byproduct. So that's about it. That's esters. For this, sometimes NaOH aqueous is used for this reaction. So alkaline conditions are, but the reaction would be fast enough. So we're just going to go through the syllabus to just double check. So acyl chlorides, esters, let me just quickly go through. So that's one. Where's the next one? So there's a lot of mention of esters. Reaction of alcohols, we did that. We did the phenyl thing as well. Ester with HCl, reaction of alcohol at room temperature, did that. So there's a lot of repetition in the syllabus. Polyesters, polymers we haven't done, so we're going to do that at the end. So we did. Yeah, that's pretty much it. That's your. Anyways, so we're done with esters. What else is left? The other thing that's left is there's probably, let me just cancel this ester thing. So this is, no, this is, yes. So most of the organic, except for polymerization, etc., I'm gonna keep that at the end. Colors of complexes, forget that. This is organic. So this one is pretty much done. What's the last? Describe the done. We're done with this. We're done with most of that. This one. The oxidation, we did the redox part, that's also done. The oxidation, we did all of that together. Relative acidities of chlorine substituted, most of that. This is one that's left. How were acyl chlorides formed? So that's just one. Let's cover that quickly. So how are acyl chlorides? Formation of acyl chlorides. Now, when it comes to formation of acyl chlorides, they form from carboxylic acids. What you do is you take a carboxylic acid and you react it with the three reactions. All you have to do is you've got to substitute the carboxylic acid OH with Cl. So a carboxylic acid turns into an acyl chloride. That's how so they form from carboxylic acids. OH in carboxylic acid substituted with Cl. So that's kind of the summary of the reaction substituted with Cl. And how do you do that? You do it, just a second, my board. So you do it with PCl3 plus heat, or with SOCl2 plus heat, or the third reaction is you use PCl5, which is slightly more reactive. So you don't necessarily need heat for that, but you can use heat. So the first two would be sufficient. Sometimes they would ask you for equations as well. I mean, very rarely. So the equation for that reaction, I'll just copy paste the equation. Plus PCl3, if we have an equation somewhere, just a second. Just one second, let me just copy. I mean, it's almost impossible to remember that equation. They've actually asked that once. So it's going to form H3PO3 and HCl or something like that. This is one reaction where the carboxylic acid turns into, so it forms HCl and POCl3. So this is the actual equation. And there's another one with SOCl2, which is, no, that's still with, that one was PCl5. This one is with PCl3. So it's kind of an impossible task to remember these equations, but you should know, I mean, at least the minimum. It's very rare that they're going to ask you about this. They've actually asked once, but this is what you should remember. What are the conditions? That's something that's commonly asked. And there's one reaction with the SOCl2 as well, this one. It ends up forming SO2N HCl. So these are the three, in all cases, you're getting the same product, which is an acyl chloride. So that's it. That's about it. That's the formation of acyl chlorides. And then if you've missed anything, that's we did the esterification. Acyl chlorides, we did the hydrolysis, the esterification. Amides we haven't done. So we're going to do that shortly because we have to study proteins. So we're going to talk about amides later. We did this phenol. We did the hydrolysis thing. So that was done. The relative addition elimination, we did the mechanism earlier. This is all done. So most of this, apart from the polymers, So amides, the acid chloride amides, we're going to talk about amides later. So recall the reaction of amides are produced. We'll do that later. Describe the reaction of amides. We did the reduction as well. So amino acids and polymerization, that's the only part that's left. And after that, you'll have analytical techniques. So polymerization is kind of it's kind of a continuation of your O-levels polymerization, condensation, polymerization, and proteins. So we'll study amides in that, and let me just because this is a new syllabus, let me just go through degradable polymers. So pretty much most of the stuff that you used to study in polymerization is no longer there. For example, amino acids, you just have to study zwitterions. You don't have to study interpret results of electrophoresis. So you don't have to study primary structures, tertiary or secondary structures. Let me just, for proteins, I think that's out. That's no longer there. So polymerization is kind of really simple. So we're gonna cover polymerization very quickly. Most of it is just O-levels. Nothing really new now anymore. And the only thing that's left after this is analytical techniques. So what we're going to do is we're going to cover in the next class, we're going to cover polymerization quickly, and then we'll start doing past paper questions. So just make sure that we have 3 boards on this. Esterification, I mean, this one, the last one, mainly broadly organic chemistry is about 3 things. It's about electrophilic substitution. Then the next thing was the comparison of hydrolysis. Then you had the comparisons of acids and bases. And this redox reactions, we did all of them. And then you had these minor reactions like formation of azodis. And we did the formation of azodis. And we did the whole ester thing. Okay, so let's continue in the next class. And I'll try and share the PDF documents for these, the notes that we have written, okay? So we'll try and do past paper questions related to organic chemistry in the next class. So, okay, everyone.
Thank you, sir. Allah Hafiz.
Okay, take care.
Thank you, sir.
Thank you.